Dear guests, good morning, good afternoon, and good evening. I hope you can hear me okay. Let me give you a very warm welcome on behalf of ABB Energy Industries. My name is Barbara Levantini-Aloi, and I have the pleasure to introduce today's session about the role of grid codes in today's power systems. The transition from fossil fuels to renewable constitutes the most profound change to power grids since humans started to produce electricity on a large scale. While distributed and intermittent energy sources continue to grow their share in the energy mix, other technologies such as electric cars, storage systems, and even buildings have come into the picture. And all these elements are changing the grid behavior with an impact on its stability and reliability. As a response, transmission system operators are reinforcing their grid codes, which are the rules and obligations to which power-generating assets must comply before connecting to the electricity grid. In this scenario, utilities, aggregators, and power generation companies must prove their fit to the requirements through detailed and high-fidelity power system simulation reports based on digital twins. Our expert today will help all of us understand and navigate this landscape. A little disclaimer before handing over to our presenter. The information we're sharing today may be subject to change without notice. ABB does not assume any responsibility for errors or consequences of software or hardware described in today's presentation. So without further ado, I'm pleased to introduce today's presenter, Giacomo Cavallini, Excitation Simulation and Modeling Business Lead within ABB Energy Industries. Giacomo, over to you.
Thank you, Barbara, for the introduction. Welcome everyone to this ABB TechTalk on grid codes. Short to introduce myself, Giacomo Cavallini. I'm working in the energy field since 7 years, working for ABB since 2012. So it has been a nice journey, 9 years already. And I'm responsible for the Excitation for the simulation and modeling related to grid code compliance topics. So to jump into the topics, so today I'm gonna introduce the grid code topic by checking the market drivers, the current trends, and what this means for the transmission systems. Then I'm gonna explain shortly what are grid codes. Why are we in from grid codes? What are the bottlenecks and some examples? But then I will dive into the simulation and modeling topic. So I will explain shortly what is a simulation model that we might hear in the grid code compliance documentation, for example, and what are typical simulation softwares and tools that are used to face those grid code compliance topics. Then, of course, I'm going to dial into the ABB portfolio. So what are we doing from the excitation system segment perspective? And there will be hopefully 15 minutes plus open Q&A session at the end of the presentation. So let's go into that. So as we know, the climate change and energy demand, they are shaping currently the energy business all in all. So on one side, governments, they are actually pushed on taking actions on reducing the CO2 emissions worldwide. And on the other hand, they have the challenge of actually supplying safely the electricity to the users of the grid. So those government actions, they are influencing the current energy mix through incentives. So the incentives are usually given to green technologies, of course. And those incentives are then, of course, impacting how the companies are structuring their strategy, of course. So one of the activities that is currently ongoing, and we know about that, is the increased install base of the renewable power plants. So this one goes with the wind power plants, with the photovoltaic plants, and also we see that, for example, hydrogen production is also coming in the picture right now, right? Then on the other side, we had the discontinuity of the conventional power generation units. So, for example, coal, they have been decommissioned and substituted by renewables, right? And on the other side, the governments are also pushing for investments into the e-mobility and to have a more sustainable environment, right? So all in all, climate change and increase in the energy demand are the key drivers for the energy transition that we are seeing right now. And this one, unfortunately, doesn't come without consequences. So one thing that we see right now, for example, is when, for example, the wind picks up in north of Germany, if we can say an example of a market, then of course there will be 10 gigawatt plus and power generation to the network. So somebody will have to ramp down the conventional to avoid the over frequencies in the grid. So what we are seeing is that, and at the moment, there are more and more noisy frequency regulation of the grid, and the decrease, let's say, in the conventional power plants is also posing a decreasing in the active power reserve that is available on the grid. So all in all, we are seeing a challenge for the frequency stability of the network. At the same time, there is a decreased reactive power reserve. So the synchronous machine, of course, as we know, they were producing reactive power, and they're able also to absorb reactive power quite quickly. And those are actually currently being decommissioned. So we are seeing that there is a challenge for the voltage stability of the grid. At the same time, there is less inertia in the network. So of course, when we talk about the big rotating masses that were part of these large power plants with 1,000 megawatt plus synchronous machines, for example, this is actually, unfortunately, at the moment, is decreasing in the installed base. So we are seeing that the network is more sensible to faults and actually requires a higher fault current contribution to be able to keep a stable operating condition. At the same time, we are seeing also a worsening of the power quality. So there is the increased use of, for example, power electronic devices like battery systems that actually generates harmonics into the grid. And this with hydrogen will not slow down. And because of this also, the power quality of the electricity of the waveform is actually worsening currently in the network. So all in all, there is a decrease of the network strength that is leading to an increase of instabilities, and therefore use of drastic actions from the transmission operators like load shedding in certain areas of the world. So everybody is running, let's say, under the covers. So there are different activities that are going to counteract those challenges in the grid. One of them is, for example, the increased demand of synchronous condensers in the grid that can provide those rotating masses and this high and fast fault current contribution, for example, to the network. At the same time, there is also an increased demand of peak shaving application. So units, small engines, for example, and small units that can start up from 0 to full power, for example, in 30 seconds. And those are used, of course, to stabilize the frequency of the grid during certain moments of the day, right? Increase also demand of frequency containment reserve. So, for example, battery systems or supercapacitors that are able to give a very fast contribution. And then there is also the rise of this green hydrogen. So basically, during the overproduction, the idea is not to ramp down the conventional, but to keep everything running and to produce also hydrogen with exceeded power. Can be, of course, island operated, but can be also operated while connected to the grid. At the same time, in other markets, we see the rise of the PSS functionalities. So in markets where historically PSS was not a topic, like Europe, a very highly interconnected network, for example, we start to see the increased demand of customers and from transmission operators asking for advanced PSS functionalities, like, for example, PSS4, multiband PSS, or even in some markets, adaptive PSS. And of course, the network operators, to avoid that the market gets wild, let's say like this, they are reinforcing the grid codes. So basically, what are the grid codes then, right? So grid codes are a set of norms and regulations that are applied to the power plants. So the power plants, they have to comply with the grid code regulation. Why? Because the grid code is specifying conditions at the plant point of connection. The point is that whatever power asset is connected to the grid, of course, will be influenced by these technical regulations. So we are talking about synchronous machine, we are talking about turbine engine controls, for example, for the frequency regulation. We are talking about excitation systems, protection relays, or even the DCS and the plant control. So here, all the equipments of the power plant that are connected to the network, they are influenced by the grid code regulations. So this applies, of course, to conventional power plants, like nuclear plants, diesel, biomass, or even synchronous condensers, actually, to renewable power plants, like offshore wind, onshore wind, and photovoltaic. But also it goes to large industrial plants, for example, that can generate disturbances in the grid, like flickering, for example, and as well to high voltage lines and FACTS, like, for example, when we have like HVDC links, those are also influenced by the grid code requirements. So the grid codes is really impacting a large, wide application. So there are many of the applications that are connected to the network, they are influenced by the grid code norms set out by the transmission operators. So what are the major challenges, let's say, that are posed by the grid code and documentation, let's say the grid code norms, to the power plants and also to the OEMs, so to the equipment providers. So one of the things is, of course, the equipment that connects to the grid code, it has to comply to it. So comply meaning that the hardware and software functionality of the equipment has to be in line with what the grid code specifies. On the other side, the network operators, the transmission operators, they are often requiring, this depends on market and market, we will see that, but they are often requiring to the power plants in this case, simulation models or mathematical models of the equipment that is connected to the grid. And this one is needed because they will use these simulation models in their large network models that in some simulation softwares to evaluate beforehand what can be the bottlenecks of their power grid. At the same time, in certain areas, not all, but in certain markets, network operators, they require from the power plants the so-called grid connection study. So it's a simulation study report, big one, depends of course by the requirements, which is demonstrating basically that the system that is connected to the grid is complying with the grid code, but on a simulation perspective. So everything is based on simulation models as well. And this one is something that is required by from the transmission operators to the power plants, or as well, this can go down to OEMs, so to the suppliers of the equipment. At the same time also, of course, the equipment that is connected will be tested. So in certain grid codes, they specify clearly which kind of test needs to be made, needs to be done on the equipment to certify that this equipment is compliant. And this depends from the different markets that's in the world, right? So here, the compliance of the plant, unfortunately, is not checked once when there is a new equipment installed or when there is, for example, a revamping or retrofit of current systems, but it's periodically checked. And this depends also on the market. Some markets, they require to have a periodical check of 2 years, other ones 6 years, other ones 4 years. It all depends on the country-specific regulations. And here some typical technical requirements that are set by the grid codes on conventional unit especially. So here, for example, they are about generator excitation, and they talk about voltage and frequency ranges, for example, for a specific time, the minimum short circuit ratio, for example, of a synchronous machine, how fast the voltage response of the system should be, for example, raise time, overshoot, and settling time. If the voltage regulator needs to be of the HIR system, so high initial response excitation system, or also which kind of damping performances the system must have. It also goes on the turbine and governor, of course. This is one of the major technical requirement block, let's say, of the grid codes. So here they really set requirements on how to control the frequency of the grid, right? So here it's about droop settings in case of over frequency and under frequencies. It can be about frequency response deadband. So for example, within which frequencies the governor control shouldn't react, for example. Power output decrease with falling frequency with gas units, for example, and frequency response capability, so the maximum power within a specified time range. So here, the turbine controls and the engine controls, they are really strongly influenced by the grid code, even more than the excitation control and the generators. Then there are certain system level requirements. So here, for example, we're talking about mostly symmetric or asymmetric faults. So in Jergo, they are called fault write-through capabilities. And this one is one of the major topic that is creating issues, let's say, in the grid code requirements, because it's a system level requirement. It's not easy, it's not possible to evaluate the fault write-through capability of an isolated system. I mean, just taking the generator, for example, it requires the modeling, a decent modeling, let's say, of the plant. So this one is one of the major issues usually. And nowadays, certain markets, they have quite strong fault write-through regulations. And those depends also about how fast, for example, the protection systems normally reacts on the grid. So this is really coming from the network operations, from the transmission operator, and are posing quite some challenges on power plants and OEMs. So here, I mean, it's a kind of worldwide map, let's say, of the grid code regulation right now. We know, for example, that in North America, it's quite established. I mean, there is a NERC standard, for example, there. We have Colombia is a strong market related to Greek code, where, for example, model validation is highly required. Germany right now, as we know, and Australia, they are very strong markets as well. I mean, Australia, they have specific process with the R0, R1, R2 phases. For example, in Germany, we have the VDE and the FKW standards, for example, that are really setting the requirements on the modeling. But we are seeing that currently there is a push towards stronger Greek code regulations. For example, Italy now is becoming a hotspot for Greek code. Spain is also coming. And we also see that African regions, for example, in African markets, they start to adopt stronger Greek code regulations. So Africa and also Central Asia. So all in all, Greek code regulations are getting stronger and more complicated on a worldwide level. So we dive into the simulation and modeling. So what is a simulation model? We just mentioned it before. I mean, this looks like here like a single line diagram of a power plant. Well, it is actually. It starts with very simple modeling. So we just place some transformer models, for example, on the grid. So it can be step-up transformer with on-load and no-load step changers, can be auxiliary transformers feeding some loads of the plant. But the major point for the Greek code compliance goes with the power generating modules or units. So here, it seems like just a synchronous machine. Unfortunately, it's not. So here, that power generating unit is made up simulation models. And here, of course, we have the voltage regulation on one side. So we have the excitation system and exciter machine mathematical model. We have the synchronous machine model here. And we have, for example, governor and turbine models and controls. So this one is normally the frame, if we can say like this, of a power generating module. There can be also here the protection relay together with it. My come depends about how the company making it or how this is made by the different consultants or different companies. So here about synchronous machine, when we talk about synchronous machine model, normally we are talking about IEEE equivalents or equivalent for the differential equations, of course. So here we have the equivalent circuit of the synchronous machine. On the other side, it can be also described in block diagram and in functional blocks. Like, for example, the GenRho or the GenSal. There is a very famous model typology that it's used also quite often in North America, for example, or in other markets. Now there is also the GenTPJ. But here, mostly the parameters of the model. So the model itself is a standard library, usually of simulation softwares. And the parameters are normally given by the generator suppliers. So that's normally the approach there. When we go instead to excitation systems, then things get a little bit more complicated because this depends on the supplier of the excitation system. So now, for example, let's take ABB excitation system group. We have our Unitrol 6000 excitation system and also Unitrol 1000 excitation system. Already by considering them, we have two different models. So for the Unitrol 6000, for example, the excitation system can be modeled with IEEE equivalents. So of course we have a part which is the voltage regulation. We will have a part that is the PSS and other ones that are over excitation, under excitation, stator current limiter, for example, and indirect power factor regulator, for example, or Q regulator. This is typical. IEEE 4215 2016 has quite good models already compared to the previous version 2005. Unfortunately, in some markets, like for example Australia, or like nowadays also in Germany or in other markets like South Africa, detailed custom models are required because not always the IEEE equivalent can represent the excitation system, for example, the excitation system control in a reasonable way. So here in those markets, detailed models are required. And for example, for the ABB excitation system, at least, we have developed those models and we have the user-specific models, detail-specific models of our equipment, Unitrol 1000 and 6000. And the excitation system model includes also the rotating exciter, if it is a brushless excitation system, because according to IEEE definition, the exciter machine is part of the excitation system. So the model is including that. Similarly, as the excitation system, we have also the governor part, right? And the turbine control and the turbine model. So here also there is a large documentation, let's say, on standard equivalents, let's say, of the mechanical driving system. For example, IEEE PES, sorry, not PEC, PES Tier 1 is quite a nice document where we can find a lot of models. A famous one, for example, is the GGOV1 for gas units or for gas engines, or also the gas, so of course gas unit. But there are also many governors for the steam units like the TGOV5, TGOV1, and hydro units as well, which are depending, of course, on the type of turbines that we have, Kaplan, Francis, and so on. So here, simulation softwares, they have a large libraries that is including those models here. But also in this case, in certain markets, user-specific models are required. Usually for fault rate through, for example, the dynamic models of the excitation system is strongly requested because the behavior is quite fast. So during the fault, I mean, the excitation system will push, the generator voltage will push it up. So there will be a strong influence. While, for example, for the governor part, it may be that it's very slow acting. So it's not really playing a big role during fault rate through, and fixed torque control can be considered. But this is not always the case. So, for example, in North America, standard libraries of PSSC software, for example, needs to be used for the governor part. And those governors here are, of course, most of the cases part of those standard libraries of the softwares. And here we talk about the software. So what are the typical state-of-the-art softwares that are used for Greek code compliance services or for Greek code compliance scopes worldwide? The market is highly fragmented. There is a market leader that is PSSC. I mean, PSSC is a quite famous software that is used for RMS studies. And for example, in North America, is established, Middle East, Australia, so Eastern Australia especially, and Southeast Asia. That's also a tool that is strongly used. We have Power Factory that is gaining quite a lot of power, let's say, and speed in Europe for the German. Due to the German market and the component certification and unit certification is there, but it's also strongly used in South America, in Africa, and Central Asia. We have PSCAD used in North America, North Europe, and also Eastern Australia for EMT studies, while Power Factory can be used for RMS and EMT studies as well. Then we have ATAP in certain markets as well, North America, Europe, and India. And there are also other tools like MATLAB or NetPlan that can be used. But normally, when we face Greek code compliance topics and the discussion with the network operators, in most of the cases, requirements are set on the PSSE or on the Power Factory or on the PSCAD. For example, that's typical for Australia, where PSCAD and PSSE, for example, is requested by IMO, right? While, for example, South Africa, ESCOM is they use actually Power Factory. So what are the most common simulation required prior connection? I mean, here the market is wild, then strongly depends about the regulation. We can go, of course, from static analysis like load flow studies or harmonic studies, or also eigenvalue studies, I mean, for small signal stability, like for example, the plot to evaluate stability, so the oscillation modes and how stable or unstable they are, how damped. These one, the eigenvalue studies, they lose interest when we have just small models into the grid. RMS dynamic simulation. So here we talk about governor, for example, power set point changes, fault rate through, like said before, large voltage changes at the point of connection for the reactive power capability, for example. So the simulations can be quite wide and can be done on a different perspective, let's say, depending on the power plants. And then here, then we go, of course, also into the frequency domain analysis. So that's typical, for example, in certain markets. The transmission operators, they require the transfer function study of the equipment. So this, for example, is about the excitation control system when it goes into the voltage regulation analysis off grid, for example, when the GCB is opened, or also about the generator excitation plant. So this one is more about the transfer function of the full unit while it's connected to the grid. And here you have also some influence from the network, for example. So these are typical simulations that are required for the Greek code compliance, and this depends on different markets. So every market has its own different requirement. So we make the example of UK now, for example. So here we have for the type B, C, and D power generating modules. which depends also on the size of the generator and on the voltage at the point of connection of the plant. So here, for example, we need to have some voltage fluctuation and flicker studies and harmonic studies of the power generating unit, as well as the reactive capability. So here, active power capability, basically it's about a variation of 5% of the voltage at the point of connection. Limited frequency sensitive mode for over frequencies and under frequencies are also done normally. Fault right through studies with 140 millisecond three-phase fault. It's also typical required, as well as the model validation. So here it's about overlaying simulations and measurements from site to verify that the models are accurate. And this is done with normally with step responses. So off-grid step responses and on-grid step responses. So here also test, typically, I mean, there are some tests also required, as I said before, and here the tests are going mostly into the direction of doing, for example, voltage step changes of the excitation system, comparing those step responses I said before for the model validation, to check the open and short circuit saturation characteristic of the synchronous machine, excitation system on-load test, for example, 1 or 2% step responses of the voltage, and to verify the frequency response, for example, of the governor. So those are typical examples, and that's the UK grid code, and the engineering recommendation G99 are giving a nice overview of that. So the important points to consider for the grid code compliance is that every excitation system, every engine, turbine, and protection system suppliers, they will have different models that are representing their equipment. And the levels of details required is depending on the grid code. So Australia, Colombia, Germany, Mexico, South Africa, and Denmark, for example, the detailed models are normally used and are a must. While, for example, for North America, UK, Argentina, and other countries, IEEE equivalents might be enough, for example, for the studies. And for many other countries, it depends on the project and shall be evaluated on a case-by-case basis. This depends really about the country. PSSE was and is still one of the most used power system simulation software worldwide, but Power Factory is at the moment growing due to the outbreak of the German market. So many countries do not specify which simulation software to use, but they just say that it must be a recognized software. So for the company performing the study, better to use, let's say, a state-of-the-art software recognized by the network operator. And the simulation are often similar in different countries, like for example in EU when we have the ENSOE standard, but sometimes it might be quite different also. Like for example, Australia, it's quite different comparing it with the European countries. And everything depends on the applicable grid codes. So about ABB, so what are we doing, right? So from the segment excitation, we are providing those plant simulation solutions for our customers. So we model the plant equipment from every kind. So we can model the power generating module, so conventional power generating module, but also a renewable, for like a wind park, for example, or a wind unit. And we optimize, for example, the control system. So we optimize excitation system, we optimize the AVR of the excitations, we optimize the PSS and the limiters also to ensure that the grid code compliance is achieved. And we perform those simulations that are packed in the study report that will be provided to the network operator, or that can be provided to the network operator. All those simulations then, we normally perform validations. So we validate that the models used by us in the simulations are accurate and represent the behavior of the system. We also developed excitation system simulation models, and we offer this to our customer. And this goes, like said before, is a detailed model of the Unitrol 1000 system and the detailed model of the Unitrol 6000 system. Those are implemented in different softwares, so Power Factory, MATLAB Simulink, PSSE, and PSCAD for the Unitrol 1000, while Power Factory is the main tool for the Unitrol 6000. And then we have our field service engineers that can perform the full grid code compliance testing for a generating unit, conventional unit mostly, and they perform AVR and PSS testing, as well as the limiters, the model validation test required for the validation of the mathematical models used, and they can perform also this transfer function testing. So they bring at site injection units that are used to inject a random signal, for example, into the equipment and to verify the response of it. So to have a transfer function of the equipment that connects to the grid. So they can also perform the full grid code compliance testing. And normally, how is normal project performed is that we from ABB, we collect all the requirements and all the data of a power plant. We are then creating an equivalent model of the power plant into a simulation software. We mostly use Power Factory for it. We then perform those system optimization to optimize the AVR and the PSS and everything that relates to the excitation system specifically. And after this, then we perform those simulations mentioned before that are needed as an evidence to verify grid code compliance of a plant. And all this is then packed into a grid connection study that is delivered to our customer and that can be used for the network operator. So the customer, the power plant, they can then send this report to the network operator to get an approval prior connection and to proceed for site testing. Then site testing comes, and here then we support with our commissioning engineers that performs the compliance testing for the equipment, and they provide to us back in the office, let's say, the measurements that are used for the model validation. All over this process, then we provide our project management services as well. So we manage, let's say, the full grid code compliance process to make life of our customer easier. And one of the typical challenges is that, especially for brownfield applications, so for retrofit projects or for old installed units, data are missing. For example, synchronous machine data are missing. That's typical. And in such cases, we then send our commissioning engineer to do preliminary tests that are used for a preliminary model validation of the equipment. So then we can ensure that whatever we do after is then correct and is in line with the expectations, let's say. Additionally, from our excitation system segment, we also offer our real-time simulators. So basically, we have a device called SMTS-RT that is basically simulating a conventional unit. So it's simulating a synchronous machine and an exciter machine, transformer, and an infinite bus. So that's a single machine infinite bus system. And we connect via hardware, via copper, let's say, our excitation controls. And these are used for real-time simulation. So basically to really verify how the excitation system behaves. And we have both Unitrol 1000 hardware in the loop, and we have also Unitrol 6000 options. And all this is remote. So basically you from your office or from your home or from your room can connect remotely to the simulator and can test your excitation system. You can verify that your excitation system is, or let's say the Unitrol system is in line with your expectations. There's also some of our offering. And some examples, let's say now to finish off projects. So recently, for example, we did a full South African grid code compliance of a large hydropower plant. And we did all the simulations for the excitation system. We simulated all the required test cases by the GCR3, for example, of the South African grid code. And we performed the model validation. So we overlaid measurements and simulations to illustrate, let's say, to show to the network operator that models are accurate. And as you can see here, the results were pretty good. So here the study report was approved within two revisions. And our commissioning engineers has been also sent at site and did a great job and commissioned the unit in line with customers' expectations. Another example, it's a project with a Unitrol 5000 system. So it's a still ABB excitation system and with the TGO5 governor control. And here we modeled the full power plant, 8-machine power plant with the protection relays as well to verify that the performance is doing automatic reclosing cycles and doing fault right through were in line with the grid code. And here also grid code has been passed successfully with few revisions of reports, and the commissioning engineer was also at site. Yeah, and that was it from my side. So I would say that we can go for the Q&A. And sorry for the inconvenience before, of course.
No worries, this happens. Yes, we have a few questions that have come through. Just 1 second, and I'll share them with you. Okay. So let's go in order. The first question that came right at the beginning of your presentation was about Harmonics. So will it be convenient to use motors connected to synchronous generators to avoid issues with Harmonics?
Well, I mean, you're talking about PWM, so I believe you're talking about a drive system controlled with a rectifier inverter unit. I mean, there your system will be connected to the bus of the power plant. I mean, it will generate harmonics, whatever it is. Of course, if you have a huge unit in parallel that is giving a pretty good contribution to the waveform, then of course overall you will have a better harmonic let's say a lower harmonic intake, let's say, of the signal. That's clear. But here it's about then really the technology, the PWM technology, and which kind of drive system you connect there, right? Yeah. So I hope I answer your question. Yeah.
Thank you, Giacomo. Second question is, do the compliance testing requirements happen on the actual system or on a test system?
So here it's on the actual system. So in most of the cases, so let's take now, for example, Australia, the tests are done at site during the first connection of the unit to the grid. Or let's take, for example, Germany. They have a quite complicated process, if you can say like this. So certain tests can be done for a unit certification, so-called unit certification in the factory. But at the end, there will be always the need of a site test with the real equipment. So normally, the tests are done with the real unit at site, not a test system. Yeah.
Thanks. Then we continue with a question about the simulation models. On which platforms are the simulation model built, and how is the integration done between the models and the DCS?
Good question. So as said before, I mean, I was illustrating the slide with all the different tools that can be used in the market, right? That are used in the market, PSSE, Power Factory, and so on. So those are the platforms where the models are built. So for example, let's take Power Factory now as an example. There you can build models. It's so-called DSL model with a logic diagram, you know, by having Laplace blocks and also logic blocks. And there actually you can integrate, so you can create a model of your DCS that controls the power generating units. So that you can do in Power Factory. And for example, when we take the example of Italy, I mean, in Italy, Terna is requiring the SART system. So SART system is basically a voltage regulator, a specific voltage regulator for the plant that is controlling the high voltage busbar voltage level by sending specific reactive power signals to the excitation units. And in that case, in Power Factory, you can model that. I mean, you can create a SART system model equivalent that is connected to all the different units of the plant that is sending a specific reactive power set point. So this is possible. And in Power Factory, for example, it's a pretty good tool and nice tool to build up such models. Yeah.
Thank you. Then we have a couple of questions, very similar, about renewable generating sources. So what about the models for renewable generating sources? And do you provide this kind of grid code compliance studies for upcoming plants, solar and wind specifically?
So this one is, for example, something that it's grid code. I mean, we are hearing that mostly because of the renewables, and certain requirements come from the wind field, if we can say like this. So models for renewable generating sources, there are a bunch of. So it's full of equivalent models in the standard libraries also of the various tools that can be used for modeling renewable plants. So that's quite typical. It depends, of course, about the technology. If it is a double-fed induction machine, a synchronous machine with a converter, induction machine purely, let's say, it depends really. But those are still part of the plant model, the overall plant model. And for example, typical thing is that in the software, let's say you set the GPS coordinates of your system. and there would be a database with wind speed, for example, at specific time of the year, and such things. So you can actually do the so-called quasi-dynamic studies, where you can really simulate, for example, how much production, how much electricity production there will be from a specific wind power park, for example. So that's possible, and the models are there. So in Power Factory, for example, most of the cases, the static generator is used for that, which is basically just a voltage and current source. And behind, there is a full dynamic model of the wind, the wind unit. That's possible. And for the studies, yes, so we are also performing studies for renewables. That's also our intention from ABB for our sustainability, a sustainable and green strategy. So we want to go there also, and we are doing that already actively with some of our partners.
Thank you, Giacomo. I mean, there are a lot of questions coming in, so your presentation has really been interesting to our audience. Great to hear. So let's try to cover as many as possible. In case we won't manage to take some questions, we will answer to all of you privately. So the next question is about virtual power plants. Which role virtual power plants can play in the grid code?
Very good question. So, I mean, digitalization, right? So there is the topic. Nowadays, 2021, so we would expect that digital technologies or digitalization is providing a good contribution, let's say, for the network stability. We know that some companies, or somebody is trying to improve, let's say, the overall network performance with artificial intelligence and machine learning algos, for example. Virtual power plant, it's for sure something that is very interesting for the grid code compliance, because for example, it can give live status of compliance of the plant, right? I mean, you can trigger trend, for example, specific network events, and you can say, yeah, this has been grid code compliant. So for the periodical grid code compliance scopes, I mean, it would be quite nice and easy, for example, for transmission operators and power plants to have a seamless, let's say, communication, right? And that's also, for example, ABB, we have Optimax, right? And that's something that it's also for virtual power plant applications. And this one is really something that, let's say, in the future will be interesting to see in the use for the grid code compliance. Let's say this. Yeah. So definitely, overall, having a large, let's say, worldwide virtual power plant is definitely something that can improve the overall network stability on the longer run. Yeah.
Thank you, Giacomo. So next question is our guest is asking you whether you can define the steps for component, unit, and system certification and typical turnaround time from project start to reporting. I guess this is quite a complicated question to answer with just one specific answer, but let's try.
Yeah, I mean, it's I believe that the question is related to the German market, most probably. And there we have this component certificate, this component certificate. We have also this Einheit certificate, the unit certificate, and the Einzelnachweisverfahren, this itemization process, so-called like this. And it depends. For big units above 20 mega, for example, this itemization process is normally done. So it's not possible to do a fault right through case on a 300 mega machine. There is no test equipment that can withstand it. So normally the verification is done at site. So this system certification, let's say like this. When the units are small, then the Einheit certificate or the unit certificate can be done. But then, of course, there is special testing equipment that needs to be used for that. Honestly said, that the project can be, I mean, the process can be quite long. So now I would say like this, then we kick these details, let's say, in an email for the how long the process is and the details of the process. So Baba, please take it for a second clarification, let's say this.
Perfect. Yes, we'll do that. So we continue. We still have, for sure, at least a couple of questions we can cover. So next one is, what shall be the accuracy between simulation result and the actual site test results?
Also, good question. It depends about the Greek code. Certain Greek codes, they have specifications. So like accuracy band, where basically the simulation and the measurements, they have to really be overlaying more or less. So they have an accuracy band. Other ones, they don't. And this one is really led to the sake, let's say, of the results. If looks, I mean, it sounds like reasonable or not. So depends upon the norms. Germany, for example, they have clear requirements on the measurement band, or let's say the accuracy band. Australia, they have clear requirements. It depends about the market. For example, South Africa, not really. And that is really about the sake of how well, let's say, the overlaying is going. And it can be a discussion point with the network operator when the company thinks, no, it was good, no, it was bad. This is like, it's a fight point, let's say, like this between the two organizations. Yeah. So I would say check the Greek code requirement. If nothing is written, then it's led to the people seeing the report. Let's say this.
Thanks. So let's continue. Next one is, after modeling and validation of a power plant, do you think that it's necessary to perform time-based tests to validate the models again?
Good question. I mean, normally this is not done, right? I mean, normally then the simulations are performed again. The network changed. So that's something that, I mean, the model, of course, of the network is changing in time. This is not fixed. We know that. And some equipment is degraded or degrading in performances, but the model itself, the control structure will always be the same, right? For the excitation system, regardless if it is today or in 10 years. I mean, that will be the control structure. So model validation there is not needed. While for the network, yeah, then that's something else, yeah. But most of the case for Greek code compliance, the network is modeled as a infinite bus with reactances or with the equivalent impedances, min max usually, depending on the short circuit power, and that short circuit power, of course, will change in time. So that's why periodically the plant needs to be checked if it is still Greek code compliant. But for the model validation, only if a new equipment is installed, I would say like this.
Thanks. So the next question is testing your knowledge of the Australian grid code. So let's see. So what makes Australian grid code so stringent? Can you give some example of technical parameters which are more stringent than other countries?
Yeah, for example, already the process, I mean, the R0, R1, and R2 phases are quite specific. But when we talk about parameters, I mean, let's take the PSS, power system stabilizer. In Australia, they specify that the damping ratio of the system with PSS has to be higher than 0.1 for every oscillation mode. I mean, that's something new, right? I mean, that's something quite specific and quite difficult to evaluate. I mean, it's not written in any Greek code, That's just an example, but for example, the PSS is quite strong. I mean, the requirement in Australia. If you can just give an example.
Thanks. You passed the exam.
Hopefully.
So next one is, on what basis one model is selected from the standard libraries amongst the others?
Yeah, this depends about the accuracy of the model. So, for example, in the past, there was this IEEE 4215 2005. And the models were basic, So many times the equipment was more advanced than the model itself in the IEEE, and the IEEE model was not really representing well the real system. So in such cases, the detailed models were used. And nowadays, the new IEEE has quite good standard library, I would say, of models. So in most of the cases, IEEE equivalents can be used, but it depends how well the IEEE represents the detailed equipment. And normally, it's not about the regulator block itself. I mean, if it is a PID or any kind of control, it goes normally about, for example, the excitation limiter logic, or for example, if the governor needs to have some specific emergency shutdown logic, such things. So these are really something that depends about the equipment that you install and the IEEE equivalent that is used for that equipment. Other way also, certain markets like North America, I mean, they specify a list of accepted models. Sorry. So it's not possible to go around that, right? Yeah.
Thanks. Let's see if we manage to take another couple of questions. The next one is about one of our products. So can we use the Unitrol 1020 simulator setup for motor excitation training?
Very nice. Yes, I mean, it's possible. The SMT-SRT has an option for setting the machine as a motor. So it's possible. Yeah. So I would say that this question we kick for a second stage. I mean, we can send maybe some documents about that. Yeah.
Perfect.
We have also this remote simulator, I said before, so you can access it from your room, wherever you are, which is not that bad, honestly said, I think. So yeah, that would be an option.
Okay, next one, back to the renewable theme. Are there initiatives for new renewable installations requiring detailed studies to confirm stability prior to construction, as well as taking into consideration the forthcoming reduction in large fossil unit on the system?
Yes, so that's typical, and as well, it's typical that, for example, in certain regions, the network operator they agree, let's say, on the installation or the connection of the renewable power plant if they put a clause, if it is not negatively degrading the grid. Yeah, but this is difficult to evaluate, right? I mean, as a power plant or as an equipment supplier, you will need to have the model of the grid. So that's why there is a need of these grid integration studies, let's say, or where the power plants then are, or the performance of the renewable plants are then checked, and of course also their effects on the network are also checked. So that's typical, yes. Yeah.
Perfect. Next one, if we're using tap changer control for the reactive power control, do we need to normalize the tap position? And if so, when do we need to normalize it?
Yeah, well, yes, of course. So I believe you're talking about on-load tap changer. Most probably, I mean, if you have no-load tap changer, then it's clear. It's fixed during the RMS study, right? I mean, but if it is like a on-load tap changer, then when you initialize with the load flow, with the initial load flow condition, then you will be able to set the initial condition of the tap position. And then if you have behind the tap control, if you have an all-load tap changer, then you will have a control loop of the tap changing technology, let's say like this. So there you will have to model this control structure of the tap changer to have a decent dynamic response. Of course, it's going to be slow. So if you have a fault right through, there will not be effect. But if you have like a 90 seconds voltage drop on the grid, then that's something, yeah.
Okay, we just have 1 minute, so I'll pick one of the remaining questions. Is it possible to validate models of a power plant using only network events data?
Well, you would have to, yeah, you would have to create the model of the plant and overlay that measurements or that event measurements with an equivalent simulation. Possible, yeah, it's possible. But normally the Greek code requirements is that you validate that during commissioning or right after the commissioning. So yeah, usually it's really a set process, You have to check with the network operator, I would say this. Yeah.
Perfect. Thanks a lot, Giacomo, for your great presentation and for taking all these questions. There are still a couple. And as said earlier, we will come back to you. We see who's asked what, so we will be able to answer each of you. Also, some questions have come through the chat about receiving a copy of this recording. As said at the beginning, you will receive in the next couple of days an email into your mailbox with a recording of this session. This session will also be uploaded on the ABB Energy Industry TechTalk page, where you can also find other sessions on other technologies, but also other sessions about excitation. So let me once again thank our presenter and thank all of you for being with us today about this topic. We will have more sessions deep diving on the grid code compliance studies. So stay tuned, you will receive more invitations in the future. Thanks again for being with us. Thank you, Giacomo, for your time.
Thank you, Baba. Thank you, guys. See you next. Bye.
Bye. But before we get started, let's take a quick look at the logistics of this webinar. All participants are on mute. Should you wish to submit questions, please use the Q&A box that should be located at the bottom of your screen. We will have a dedicated session at the end of the presentation. As you may have seen, the presentation is being recorded and all participants will receive the recording via email in the coming days, and it will be also made available on the official ABB Energy Industry TechTalk web portal. Also,